devices die on us. And mic? Oh. Okay. Well, we all know the hassle of having our mobile devices die on us, and of losing our chargers or having them break. And we depend so heavily on our electronics in this day and age. How is there not a better method of keeping our devices alive? Well, maybe there is. Maybe the next time you walk into a coffee shop or an airport and you get free wireless internet access, you'll get free wireless charging to power your mobile devices. We are Team Tesla. My name is Anuchella, and with me presenting tonight are Ben Phillip and Patrick Healy. We believe that this technology is in our not too distant future, using a novel wireless power transfer method called time reversal. So first I'll begin with a description of what time reversal is. It's a short technical primer that will lend some insight into how we achieve wireless power transfer. Then, Ben will discuss where we are in our research and where we hope to go. Finally, Patrick will conclude with our team organization and some advice for those who are at the beginning of the research process. So, time reversal is a signal focusing technique. You can think of its purpose as responding to a received signal and communicating with the sender, and only the sender. So for example, here we have 2 points A. You can think of these as a model for an antenna. And these antennae would send and receive signals. So if A sends out a signal and B listens to it, B can then respond to A and only A, since the signal converges at that point alone. So if we take a look, there's A sending out its signal, it's reverberating in the space, and then we're listening at point B. Now point B has that signal, and all we have to do then is take that signal and reverse it. We're just flipping it. That's what time reversal is. It's reversing the signal with respect to time. There's no sci-fi involved. So now, because waves have reciprocity, what that means is that we send a signal from A to B. If we reverse that, we can get that signal to go from B to A. And that's what we see here. We're sending it back the reverse signal from B, and it's all converging right back onto point A. And there we have it. The original signal back at A with a little bit of noise, but a very recognizable shape. Now these are all the steps together. There's the reverberation, where we go to the reversal of the signal, and we're playing it back to get convergence back at it. That's our original signal. So that's the method of time reversal. And this is how we organize our study of this process. Well, the first step is we identify our goals. Our two goals are to enable usable transfer efficiency. What that means is basically we just want to get a good ratio of the power that we input into a cavity or into a room, and we get a good output at your device. So we want a good ratio there. And then our more short-term goal is to light an LED using time reversal. It's just a visible indicator that the process works. So then we kind of go into the scientific method. We identify related parameters. We conduct smaller experiments. We compare our hypotheses to the data. So really we're just looking at our results and do they match up with what we thought would happen. And if not, we refine our experiments. It's all very cyclic. And with each iteration, we're getting more and more focused. And then there's a lot of back and forth with our goals. So it's a very flexible process and it's finely tuned to our purposes. So now that you have an introduction to our theory, Ben can give you an explanation of where we are in practice.
So the point where you start for any good experiment is a solid model. And that's what we have here is a basic testing environment, a CAD model of sorts, but for simulations that we can run. It's a 2D simulation. You send a signal in at port A that looks like this, a simple sine wave pulse. And you send it in this simulation, bounces around, it hits diodes 1 and 2, which do a funny thing with the frequency. It doubles it in most cases, called harmonic generation. We collect the data at point B, and then do the time reversal process like you saw on the previous slide. Now when you measure what happens at diode 1 and 2, you get power, and this is the simulation result that you see from that process. As you can see, diode 2 doesn't have as high peaks as diode 1, so we need to work on the model a little bit more, but we can see that the theory works. Fortunately for us, we've been able to replicate this in a real experiment using a 3D environment called a gigabox. What you see on the screen is a 2D cross-section, top-down, of our testing environment. We put an input signal in at A, much like you saw on the previous slide. It goes through B to a frequency multiplier, which we needed to use to behave like a diode would to generate harmonics, which comes back out at C, continues to bounce around in the box, and we collect it at D. As you can see, we have that signal called the SONA that shows us where C is in the box. Then when we want to reconstruct, we send that signal, reversed in time, like you saw in the animation, back into the box through D, where it should reconstruct at C if we only use the harmonic that was generated. And as you can see, we have a decent looking pulse here, and to make sure that this isn't happening just anywhere in the box, we show that it isn't happening at A. And as you can see by the scaling, the amplitude is about 1/2 that of the actual reconstruction, which is very good for us. If we were going to try this again without using another frequency, we would just remove ports B and C and just send the signal in at D and measure at A for simplicity's sake, which is what another section of our team did to test efficiency. First they tried sending in a single pulse and collecting the data and then performing time reversal on it, and they get this nice looking pulse here on your right. Then they tried to iterate these pulses and overlap them so that they could compress the amount of time it took to run and get a single pulse to a shorter amount of time. And as you can see, it continues to reconstruct in a smaller amount of time. And future tests will look to see if there's an optimal time delay between the signals we send out for the power we're able to collect at that port. This is a model of a rectification circuit that we hope to use. As you saw, that pulse that we get at the end is both positive and negative. It's an AC signal, and you can only charge a phone or iPad, whatever, with a DC current. So this circuit will make it into a DC signal and smooth the current. And as you can see, this is a simulation of how such a circuit would behave. And a circuit like this is important because it allows us to see what properties we need in the diodes and the other components that we need to create this system. And now we'll have Patrick to talk about that iterative process and the change that your projects will go through throughout your time in Gemstone.
Thank you, Ben. My name is Patrick, and like Ben said, I will be talking about how our project has changed. Our project has changed in many ways, and also in many ways we try to encourage change in a lot of different aspects of the project. So first off, when we first proposed this project, we were trying to focus on time reversal as it applies to a moving object. So we were trying to move high amounts of energy to a moving object, such as an RC car. We rather rapidly found out that this was a very lofty goal that required a great deal of preparation that we didn't have ready yet. So we refocused on a smaller goal that's getting stable amounts of energy to a much smaller load in a much more efficient way. And in this case, we're just using a simple LED diode because that gives you a very strong, either it's on or it's not. And then also, you don't need a great deal of energy to get it to work. So here we can test our efficiency, which will then allow us to, later on, us or perhaps other people who follow after us, move it to higher power and then eventually moving it to moving objects. We also focus on the idea of change in many of our other aspects of our team. So first off, the team has two major groups. We have the non-research groups, which are focused on sort of the back end of making the team work. And then we also have the research groups, which are doing the nitty-gritty. Everyone tends to be on one or both of the groups. Now, in the spring, our research groups were very broadly focused because we were trying to do the very lofty goal of having high amounts of energy to a moving object. We realized that, however, this created two vague goals for the sub-teams, and we wanted to try to narrow that down. So, in the summer, we dissolved some of the teams that perhaps were not making progress or weren't ready to do their research yet, and we refocused on time reversal itself and how we can make that more efficient for the purposes of moving energy. We then continued this process into the fall, refocusing again, discarding teams that weren't useful, shuffling people around so that we ensure that everyone was doing something they found interesting. And come spring, we'll reshuffle again and make sure that what we're doing applies to our project. So, tips for new Gemstone teams, that's you guys out there. First, as noted, research takes time, and you're going to have to go through a lot of small steps before you get to your final goal. You should you should keep the final goal in mind, but you should also make sure that you're doing reasonable research. It's a lot like climbing a mountain. You have little base camps that you set up, and not only do the base camps give you something to fall back on in the event you have issues, it gives you the experience needed to make that next climb. You can't climb all the way to the top in one sitting. Second is that meetings should further your research. They should not, stand for research in and of itself. We, in our first semester, we had major issues where we would debate research a great deal, argue bureaucratic issues, and then outside of the meetings, we didn't actually get much done. We were all really angry at each other because we argued at all of our meetings, but for all that arguing, nothing was created. So after we tried to make our meetings more research focused, and in fact sometimes our meetings are just going to the lab and playing with stuff, we've been able to get more of a momentum going, which I think is very important. So having and maintaining momentum is a very good thing. And then finally, remember that experimentation, is and should be experimentation. You don't know precisely what's going to happen, so feel free to play around with things. If you're not quite sure if something will work and it doesn't cost you anything to do it, do it. Worst comes to worst, you now have more experience in your topic, but hey, you might find out something that you weren't expecting, and that is where science is created, where you aren't sure what you're doing. I personally would encourage you all to keep Miss Frizzle in mind as a role model for your Gemstone teams. But it's just good role. Whatever. So, that ends our presentation. What we've discussed is how time reversal works, some of the research we're doing in applying time reversal to getting wireless power to be created, and then how we organize our team, to get our research completed. I'd like to thank our mentor, Dr. Onlaga, for not only giving us mentorship on this phenomenon, but also for giving us the lab equipment needed to do our testing. It's really streamlined our experimentation process and allowed us to do a lot of the sort of crazy, just see what works, that I think has worked so well with us. We'd also like to thank Mr. Bo Zhao, who is a grad student who works in Dr. Onlaga's lab, who has been able to help us with a lot of technical issues and troubleshooting. We couldn't do it without him. And then we'd also like to thank Ms. Nevenka Stravkovska, I think I just butchered your name, I apologize, for helping us understand how to do research effectively and how to really get an idea of what the field looks like. Because it's always going to be a complicated field, whatever you're researching, and you want to make sure you understand it. And then finally, of course, the Gemstone staff for making this entire thing possible. So, do you guys have any questions?
You said that noise was created in the time reversal process. Do you think that would make the power that's sent through this process less efficient?
Yes, to a degree. The noise is created by losses in the system. Ultimately, the efficiency is created in many other ways. Noise is more of a symptom of it than it is the cause. If most of our efficiency loss is caused by absorption in the walls of the environment.
If this does become like a viable method, how do you prevent other people's wireless signals to interfere with the
Okay, so the question was, how do you make sure that the wireless signals we are using don't interfere with other devices? There are restricted bands that the FCC designates for certain purposes. So in the event that this were to be used, we would have to have a band designated for us. So that would have to be a process thing after we show that it can work. Anything else?
How does your method compare to existing wireless charging systems?
Okay, would one of you guys like to? Yes, I'll have Scott take it.
So currently, there's only a couple of methods of wireless power transfer. The most notable are little charging pads that have called key devices in them, or Kai devices. And these require intimate contact around 1 to 3 centimeters, and right now they require pretty good orientation. The current new method is to have magnetic fields that will charge your phone. And even then, those only have around a 5-foot radius that they'll work in. The real difference with our process is that since it uses traveling electromagnetic waves, you don't really have a range restriction other than the loss in your environment, because electromagnetic waves are self-propagating. So in theory, we should be able to transmit substantially farther than any other method, and we have not come across any other application that has been able to safely transmit over around 5 or 6 feet. So that's the main difference that makes us stand apart.
Any other questions?
For the time reversal process, has any research been done? You talked about point A and B, but having multiple points of energy deflection and how that affects the harnessing of the energy and also the rate at which it's harnessed?
I'm glad you asked that. There hasn't been much research done on this, and this is actually something that we've been looking at. Actually, Scott's on modeling team, which has been looking at that, so would you like to come back up? Okay.
So yes, like Patrick said, since this is a very new and innovative field, there has not been a lot of information on that topic. So one thing in the modeling team that we were working on is making sure that sending signals to multiple locations will work as efficiently as we predict. As seen in this model, we send power to 2 different diodes, and the idea is that we should be able to extrapolate this to 3 or 4 diodes, and after that we could say, well, if we've done 4 or 5 diodes, we could probably do it to as many as we need to. But we are doing that mostly in the modeling software rather than in experimentation, because it is quite difficult to track multiple signals in real life in a 3D environment, whereas in a 2D simulation it does not take very long for the simulations to be completed.
More questions? Yes?
Can you explain the rectifier circuit a little bit more and maybe discuss how you're making sure that those diodes can switch fast enough to accommodate that signal?
That is actually an issue that we've been having. Scott or LC, would you like to take it?
Okay.
Yep.
Yeah, so this circuit is, it's basically it's a full wave rectifier with a smoothing capacitor. So it'll take a sine wave. So the sine wave, oh, I'm not actually sure.
We have a laser pointer? Oh, I have the laser pointer. You look at that. The top.
So the signal here is actually a very fast. I guess if we want to talk about the switching speed of the diodes, there's a lot of different factors. You want something that's called a Schottky detector diode, which has a cutoff frequency of around in the 18 to 20 gigahertz range. So for our applications, that would be sufficient. We've actually tried experimenting with a number of different diodes and only recently come across the frequency issue. So that's an area of current development.
Any other? Yep. Oh. Yeah, go.
When you're sending the signal back, would it be strong enough to potentially interact with like someone's pacemaker in their heart if they have to walk through the area?
Another very good question, and I'm going to give it to Scott. Scott is the lucky guy today.
Okay, so this question indirectly goes into like biological concerns as well. So something that's noted is the FCC does have regulations on this in terms of how much power you can transfer through electromagnetic waves. So it's assumed that if you're within this limitation, it shouldn't interfere with the pacemaker or any kind of electronic device that's within your body. Similarly, this would mean that it's safe for your skin and any other part of your body. So as you can see, different phone models have different what's called an SAR limitation, and this is just how much you absorb in your body. Similar, this would be how much a pacemaker might absorb. So as you can see, if 1.6 watts per kilogram is the FCC limit, and these phones are currently within that limit, then it's safe to say that if you stay within this limit, you will not have any potential risk to either a pacemaker or yourself as a whole. So using this assumption and going with the idea that we have, let's say, a 5-to-1 signal to background ratio, then we can transfer around 10 milliwatts of power, which we believe is enough to, at least on a preliminary scale, turn on a diode and show that our process is working. So if we are within this 1.6 watt per kilogram limit the FCC has set, we're confident that it shouldn't have any issue with any biological concerns, processes, or internal circuitry.
So we'll take one more question. Your hand is up first.
I know that you guys throw on the diodes, but has anybody given any thought as to once you get it up into Wi-Fi, like you said previously on a previous team, what happens when like Wi-Fi crashes, like here at UMD?
So I guess sort of jumping off of his question about frequency bands, we're not actually aiming at using the same frequency Wi-Fi does. So if you imagine a Wi-Fi router puts out a Wi-Fi signal, for our system, if it were ever applied to actually powering objects, would it would have its own router effectively. So yes, the router could go out like any other electronic device. If like a power outage happens, then it won't work. So in an instance like that, yes, that would be a flaw in the system. But due to the fact that we would have to, by FCC regulations, use different frequencies, we shouldn't be dependent on Wi-Fi itself. Does that answer your question? Awesome.